Have you ever had a super fast internet connection that just chokes on one specific website? Or maybe you fire up your work VPN and suddenly everything grinds to a halt? Well, the culprit might not be your internet speed at all. It could be a single, simple number hidden deep in your network settings that's causing all the chaos.
I mean, we've all been there, right? A website just hangs, a connection times out, a download won't even start. It can feel totally random, but a lot of the time it's the exact same problem hiding behind the scenes. And today, we're going to unpack it.
All right, so to really get to the bottom of this, we're going to follow the journey of a single piece of your data, a data packet. First, we'll learn the basic rule of the road for all data on the internet. Then, we'll see what happens when that rule gets broken. We'll dive into why VPNs are such a common headache, explore the internet's own clever built-in solution, and finally, we'll uncover why that smart solution often fails so spectacularly.
So, let's kick things off with a core concept, a little three-letter acronym that pretty much governs everything you do online, MTU. Okay, so the maximum transmission unit, or MTU, think of it like a height limit for a tunnel on a highway. Every single vehicle, or in our world, every data packet, has to be under that specific height limit to get through. If it's too big, it's not getting through in one piece. It is the absolute maximum size for a chunk of data on any given part of the network. Now here's where the plot thickens. That MTU, that height limit, it isn't the same everywhere. The size of the tunnel changes depending on the road you're on. For a standard Ethernet network, you know, what most of us have at home, the MTU is 1,500 bytes. But for older DSL connections that use something called PPoE, the limit is a little smaller, 1,492 bytes. And that tiny 8-byte difference, well, it's the root cause of so many of these headaches. So the big question is, what happens when our data packet, which was perfectly sized for one road, suddenly comes up to a tunnel that's just a little too small?
You know, this question from a user on Reddit just hits the nail on the head. It perfectly captures the paradox here. If the problem is that our packets are being split up, why on earth would the solution be to make them smaller to begin with? It sounds totally backward, I get it, but believe me, it is the key to this whole thing.
So, when a packet hits a network link with a smaller MTU, the router there has to do something called IP fragmentation. It's basically the network's brute force solution. It takes a digital sledgehammer to your oversized packet, smashes it into smaller pieces that'll fit, and then sends them all on their way, just kind of hoping they all make it to the other side to get put back together.
Let's just walk through a quick example. Picture this. Your computer sends out a standard 1,500-byte packet. It's cruising along the internet just fine until it hits a router connected to a link with, let's say, a 1,400-byte MTU. That router has no choice. It has to split your packet into smaller chunks and send them on. Then, the computer on the other end has to sit there and wait for all the little pieces to arrive before it can finally rebuild the original message. And here's the real kicker. What happens if just one of those tiny fragments gets lost along the way? Well, the entire original packet is now completely useless. The receiving computer has to throw away all the other pieces it got and tell your computer, hey, send me that whole thing all over again. You can see how this would cause a huge number of retransmissions and just absolutely destroy your network performance.
Okay, this brings us to one of the most common places people run into this exact problem, VPNs. And this is where that weird, counterintuitive idea of lowering the MTU yourself starts to make a whole lot of sense.
So just imagine your normal data packet. At 1,500 bytes, it's perfectly sized for your local network. It's like a shipping container that's packed right up to the absolute maximum legal limit for the highway. Super efficient, right?
But the second you turn on your VPN, it has to wrap your original packet in another layer of data for security. That process is called encapsulation, and it adds extra headers. Suddenly, your perfectly packed container has a bunch of extra stuff bolted onto the outside, and now it's too big for that 1,500-byte tunnel. It has to be fragmented. There's no other choice. And here it is. This is the big aha moment. The reason you would lower the MTU on your own computer is to be proactive about this. You intentionally tell your machine to send a slightly smaller packet, maybe 1,400 bytes instead of 1,500. This creates some headroom, leaving just enough space so that when the VPN adds its own headers, the final packet is still under that 1,500-byte limit. You completely avoid fragmentation before it even becomes a problem. Now you might be thinking, okay, this is cool, but do I really have to figure all this out myself? Well, the people who designed the internet knew this would be an issue, so they built a really clever automated solution to handle it. It's called MTU Discovery,
or PMTUD for short. And it's basically a way for your computer to ask the network, hey, what's the smallest tunnel between me and the website I'm trying to talk to? Then, once it gets an answer, it can size its packets perfectly for that specific path, avoiding fragmentation from the get-go.
So, how does this little network conversation actually work? Well, your computer sends out its first packet with a special flag on it that says, "Do not fragment." When that packet gets to a router with a smaller MTU, the router sees the flag and knows it's not allowed to smash it into pieces, so its only option is to drop the packet. But, and this is the genius part, it sends a tiny error message back to your computer. This little message, an ICMP packet, basically says, whoa, that was too big. The limit here is 1400 bytes. Your computer gets that message and goes, oh, okay, got it, and then it automatically resizes all the future packets it sends to that specific destination. Pretty smart, right?
In a perfect world, that would be the end of our story. PMTU would handle everything automatically, and we'd never have a single problem. But we don't live in a perfect world, and this very clever system has a massive, critical weakness.
I mean, if this automatic discovery thing exists, why are we even talking about this? Why do websites still hang, and why do our VPNs still grind to a halt sometimes?
And here's our culprit. For what are often thought of as good security reasons, a whole lot of firewalls out there are set up to just block those little ICMP error messages. A network admin might see them as just network noise, or maybe even a security risk, so poof, they block them entirely. And when that happens, you get this maddening situation that network engineers call a black hole connection. Your data goes in, but absolutely nothing comes out, and you never get an error message telling you why. It just vanishes.
Let's trace the total breakdown. Your computer sends a large "don't fragment" packet. A router down the line sees it's too big and correctly drops it. That router then tries to be helpful and sends the packet too big message back. But a firewall somewhere in between blocks that crucial message. Your computer never gets it. As far as your computer knows, the packet just disappeared into a black hole. So it waits, it times out, and it tries again with another big packet, which meets the exact same silent fate. Your connection looks like it's up, but no real data can ever get through. It just hangs forever.
So, what is the big lesson here? Really, there are two ways to deal with this. You can be reactive and just let routers downstream chop up your packets, but as we've seen, that's inefficient, it's fragile, and it leads to terrible performance. Or you can be proactive. You can manually lower the MTU on your own machine. This creates that critical headroom for things like VPNs. It dodges the fragmentation penalty, and most importantly, it works even when that clever path MTU Discovery system is broken.
And that leaves us with a really fascinating final thought. In our endless search for security, when we block certain kinds of traffic like ICMP, are we accidentally building these invisible walls that break the fundamental ways the internet was designed to heal itself? It's this constant, tricky balancing act between security and performance, and it's happening with every single packet you send.